input and output, that means the inverse is going to have the point negative 2 comma 0 on it. So this point, negative 2 comma 0, is going to be on the inverse. Let's look at another example or two. I see that, let's look at the other intercept. Here's a point at 1 comma 0, so 0 comma 1 will be on the intercept. Here is a point way up here at, it looks like 2, 3, 4, comma 2, 4, 6. Looks like that's 4 comma 6. Well, let me find 6 comma 4. That's going to be on the inverse. One more. 3 comma 4 is going to be at 4 comma 3. That's a piece of the graph of the inverse. And I've reflected each of these 4 points to the point with that just flip-flops x and y. Let me pick a point down here. Let's see, let me pick a couple of them. Here's a point at negative 4, negative 4. Well, okay, negative 4 is going to stay put. Right? Flip-flop x and y, you're still at negative 4. So that will be a point on the inverse. Let's pick a point here. This one's at negative 2 comma negative 3. Flip-flop x and y, and you get negative 3, negative 2. Okay, let me connect some dots here. Believe it or not, the inverse is going to look like that thing. And it has a certain kind of symmetry with the original graph. It's actually easier for me to see the symmetry if I rotate the picture this way. See the symmetry? I'm going to dot in a horizontal line, not a horizontal line, a diagonal line, which is actually one of our toolkit functions. This is none other than y equals x, right? This is just the identity diagonal line. Sorry about all of the mess on this graph. It's a little bit hard to see all the stuff going on here. And notice that the inverse in light blue is just the reflection of the original function across the diagonal dotted line. So that a point at 0, 2 reflects to negative 2, 0, 0, negative 2 goes to negative 2, 0. It's straight across the dotted line in equal distance. Here at 1 comma 0 goes to 0 comma 1, straight across the dotted line. Again, easier to see, I think, if you rotate this way. And you'll see this symmetry every time you graph a function with its inverse, that you're just folding. Essentially, take the original function and fold the paper on the dotted line, x equal y or y equals x. And of course, points on the dotted line like negative 4, where the coordinates are equal, they'll stay put. Okay, let me go to the last page of the activity. Hope you can see this okay. And do a couple more of these problems with you. Here is a function f of x equals 3x minus 6 and another one g of x equals 1 over x. This says find a formula for f inverse of x. So this is another example of what we just did on the board, finding a formula for h inverse. Let's find a formula for f inverse. I begin by writing in equation form f of x. So y equals 3x minus 6 is just an equation for the original function f of x. Okay? Now I want to turn it into its inverse. And I can do that by writing every copy of y as an x and every copy of x as a y. And then I finish by solving for y. You can't speak and write at the same time. Solve for y. Okay, so let's see. I could add 6 to both sides and divide both sides by 3 and get y isolated. So f inverse of x is x plus 6 over 3. Interesting to note what inverses do. The original function is this line. You've given an input and it multiplies by 3 and then subtracts 6, following order of operations. Multiply by 3, subtract 6. An input in the inverse adds 6 and then divides by 3. So subtracting 6 has an inverse operation, add 6. Multiply by 3 has an inverse operation, divide by 3. And the inverse not only does inverse operations, but it does them in reverse order. So here you multiply it and then subtract. Here you add and then divide. Sometimes it's not that clear to see in the formula, but in this one you can see into it pretty well. Okay, now down here it says sketch f and f inverse on the same axes. Okay, f is 3x minus 6. That's a line, 3x minus 6, with y-intercept negative 6 and slope positive 3. Actually, I'd go through 0, 2. So a rough sketch of that line, very rough, is kind of like this. Intercept negative 6, slope positive 3. Okay, 3x minus 6. Now let me sketch f inverse. Actually, it might help me if I note that f inverse is, could be written that way, couldn't it? X divided by 3 plus 6 divided by 3. And that'll make it more obvious to you that this is actually a line. It's also in the form mx plus b. This is a line that has a y-intercept positive 2 and a slope of 1/3. Well, okay, here's the inverse. I know that if the original, this is f, went through 0, negative 6, the inverse is going to go through negative 6, 0. And note again that neat symmetry across the dotted line so that you can do this point at a time if you want. I think, let's see, I think this is the point 3, 3 right here. It's on both lines where they cross. I won't do this one for you, but g of x equals 1 over x. This has something pretty fascinating that goes on. You'll be interested to see what happens when you come up with a formula for g inverse of x and sketch them together. It's kind of cool. Let me do one more problem. Find a formula for g composed with f inverse of x here right at the end. So let me just follow the definition. Almost always the first thing, really always the first thing that you want to do anytime you see that composition symbol is to do the definition. G composed with f inverse is g of f inverse. And then remember to work from the inside out. So I've got to go up the page to the work I did earlier and find that f inverse is x plus 6 divided by 3. And then g, what's g? G is the reciprocal function, 1 over x. So the reciprocal of this, 1 over this stuff, I admit I'm maybe skipping a step that many of you would do. If I said 1 over this stuff, then a convenient way to simplify that compound fraction is to say 1 over that stuff is the reciprocal of that stuff, or 1 times the reciprocal of that stuff. So we're getting this for a formula for g composed with f inverse of x. Goodbye.